Let's review exponential functions. An exponential function is something of the form y equals k times a to the x, where a is the base. If k is greater than 0, the following is true. If a is greater than 0, then as x increases, what's happening to y? It's going to increase as well. This is called exponential growth. It looks like this. If a is between 0 and 1, as x increases and y decreases. It's called exponential decay. And I know you know all those words. Y equals e to the x is called the exponential function. There's some amazing properties to it. You've looked a little bit at it based on interest rates in the past. We're going to look at it in terms of calculus this year. Note, and this is important, that's why I put it in bold, whenever you are asked to graph an equation, you can always do what? The very basic thing, plot points. Now, always for any function I will ask you to do, you could always do that. There are some out there that that type of thing would be too hard to do, but that's much more advanced than we're going to do. All right, sketch these graphs. What I'd strongly recommend is you do these, hit pause, because you need to be able to sketch these graphs easily and not just look at mine, because when you're just looking at it, you say, okay, yeah, that makes sense, and then you forget it the next day or a couple days later. So I'm going to start with 1, y equals 2 to the x. We know they're all going to look something like this, because the a value is greater than 1. Y equals 3x, what does that do? Well, if I have a point x value here of 1, this is going to be 2 for y equals 2 to the x. If it's y equals 3 to the x, it's going to be higher than that. And if it was at negative 1, this would be at negative 1/2, and 3 to the x would be at a negative 1. It would be at positive 1/2, because it would be 2 to the negative 1. This would be 3 to the negative 1, which would be 1/3. So that one is y equals 3 to the x. Similarly, y equals 5 to the x is going to shoot up a lot faster, and it's also going to go down a lot faster. That is a curve nonetheless, though. Y equals 5 to the x. So for what values of x is it true that 2 to the x is less than 3 to the x is less than 5 to the x? Well, those are going to be the positive values. Where is it that 2 to the x is greater than? Those are going to be the negative values. Here's a quick review of your exponential rules. You can see them all there. When you multiply two things in exponential form with the same base, you can add the exponents. You divide them, you subtract the exponents. You take an exponential form and raise it to a power, you multiply the exponents. This is just a manipulation. If you have two different bases but the same power, you can undo basically what number 3 is. And number 5 is similar, except just dealing with division. And if you have a negative power, it means the reciprocal, and I was referring to that there. And I'm sure you know those. It's just a matter of refreshing your mind. Let's take a look at this and simplify it. I see 16 and I see 1/8. We need to get the same base. The base in this case would be 2. You always want to go the smallest one. So it would be 2 to the 4th to the 3x. 1/8 would be 2 to the negative 3, because that's reciprocal. And then we have 2x plus 1. Now we have the same base. It's just a matter of simplifying that. 4 times 3x would be 12x. Negative 3 times 2x plus 1 would be negative 6x minus 3. Now we have the same base, and we can add the exponents. So 2 to the 6x, 12x minus 6x, or 12x plus negative 6x would be 6x, and then minus 3. And that's it. Solve this equation. We want to isolate the 2 to the x part. in this case 2 to the negative x, so let's move it to the other side. So we have 2 to the negative x equals 3. We can take the log of both sides. Now it can be done a couple different ways. In this case, we could say log base 2 of 3 equals negative x. Or in other words, negative log base 2 of 3 equals x, which is fine. If we don't have to use a calculator, that's perfectly fine. When you're doing this, you have to be able to recognize when this log doesn't exist, though. We'll talk a little bit about that later. What if you didn't do log base 2 of 3? You could also have said, take the log of both sides, or the natural log of both sides, and get ln of 3 equals negative x ln of 2. So x equals negative of ln of 3 over ln of 2. Now, why do we use ln instead of log? Why do we use natural log instead of the common log? Well, probably the main reason in a problem like this is I have to write 2 letters versus 3. All right, the next part. We have half-life, doubling, compound interest, etc. When we're compounding n times a year, we have a to the t equals a sub 0, 1 plus our interest to the nt. Compounded continuously is when we have the limit as n goes to infinity. That gives us our e, so it gives e to the rt, where r is our rate and t is time, usually in years. Not always. You got to look at the context of the problem. And half-life, we have our initial value, our starting value, 1/2 to the t over whatever that half-life is. I want to look at this problem 3 different ways. The first thing I want to do is, let's look at what would this be for 0 hours. How much of this problem? I have a half-life, certain substances, 10 hours. There's 9 grams to start. How long will it take to have 1 gram left? Well, at 0 hours, we have 9 grams. After 10 hours, since 10 hours is our half-life, we're going to have half of what the amount we have there. So we have 4.5. Now we're going another 10 hours, and no matter what value we have, when we go 10 hours, we're going to have half of it. So we have half of 4.5, which would be 2.25. Let's look at 30 and 40. So we add another 10 hours, so another half. This time it'd be 1.125, and 40 would be half of that. Can you figure that out with a calculator? Try to work on that. 0.5625. The 0.5 part is basically our 1. The 0.6 is giving us our 12 there, and then the 2.5 is from the 5. Now, where would this fit to say about 1 gram? We know it's going to be between 30 and 40. It's probably going to be closer to 30, since this is 1.1. I shouldn't say probably. It will be. And this is 0.5, so 0.1 versus 0.5, 0.6. It's closer to 0.1. 1.1. And we could use guess and check on our calculator and come up with a more exact value. Now let's take a look at our graphing calculator and see what would we do for that. What does this graph look like? This graph, we can sketch the graph. We have, let's write the equation of it. A of t equals our initial value times 1/2 to the t over 10. And let's verify that this is indeed right. I gave you the formula. You've worked with it before. Sometimes there's people that still have some difficulty with it. Why are we dividing by this half-life? Because when I plug in 10, I want 1 half-life. I want to have a power of 1/2 to the power of 1. If I go in 20, I have 2 half-lives of the original, so that should be multiplying by 1/2 2 times. 20 divided by 2, or divided by 10 is 2. So that would be 1/2 squared, or 1/2 times 1/2. This is what kind of equation? Exponential growth or decay? This value is between 0 and 1, so it's exponential decay. So it's looking like this, and we'll have something there. So what we want to do is calculate that value. Let's see, how would we go about doing that here? Let me turn on the calculator, and let's type in the equation. 9 times 0.5 to the power of x divided by 10. And we want to see where that intersects 1s. Now there's two different ways we can go about doing it, and this is one of them, and I'll show this. What kind of window do we want? We know we're going to have 0 we know it's between 30 and 40, so let's just go out to 40. We really don't care about a whole lot of the y values except between around 1. If you want, we could start with 0 and go up to 9, and we can just leave the scales there at 1. Let's hit graph. And there we can see the intersection. Now I'll show the intersection here for the 8384. We'll go second, Calc, and that gives us our screen. And what do we want? Intersect. It asks us, we only have two functions, so the first one, hit enter. The second one, hit enter. Guess, just move it close to the intersection point. Hit enter, and that gives us our answer, 36.69925. And typically we'll go to 3 decimal places when we're using the calculator, so approximately 31.699. And this would be hours in this case. So again, we have to look and make sure we know what our units are. Let's look at the next part. Now let's take this same problem and we'll solve it algebraically. We have 9 1/2 to the t over 10 equals 1. Divide both sides by the 9. Take the ln of both sides. This exponent will come down, so t over 10 ln of 1/2 equals ln of 1/9. Now we want to divide by ln of 1/2 and multiply by 10, so we'll have 10 ln of 1/9 divided by the ln of 1/2. Now we can simplify this because this is either ln of 1 minus the ln of 9, and the ln of 1 is 0, or you could say the ln of 9 to the negative 1, and that will come down. Either way, you get negative ln of 9, and similarly this would be negative ln of 2. So the simplified form of this would be 10 ln of 9 over ln of 2. And again, that's hours. And if you plug that in on your calculator, you'll get our 31.699. All right, how much time will it take for an investment to double if the value double in value if the annual interest is 6.25% compounded monthly? So let's take a look at that. This is an important thing. I always want to see you define your variables, especially when you're taking a test or quiz. Let t equal time. That is insufficient. We need to state what the units of measure. In this case, we're going to be in years. And then here, x would be the original amount. So we'll have the equation be our original amount times, what's our interest rate? We have 1 plus 0.0625 divided by 12, because this is an annual rate and we want a monthly rate. And then we'll raise that to how many compounding periods? There's 12 compounding periods in a year. So at t years, there will be 12 t compounded periods. And we want our money to double, so we'll set it equal to 2x. The x's go away. We can take the Actually, let's just write that. 2 equals, typically for this kind, it's just easier to write it as 1. This would be 12 over 12, so 12.0625 divided by 12. Doesn't quite look as ugly as the 1 plus the fraction there. Now let's take the ln of both sides. ln of 2 equals 12t ln of all of that stuff. So then t is the ln of 2 divided by 12 times the ln of 12.0625 divided by 12. Now what I want you to do right now is take out your calculator and actually do this calculation. Make sure that you get the exact same value that I get. This is approximately 11.119 years. If you have any question on that, if you're getting a different number, ask in class and we can go over that. Here's a general way to look at all these exponentials because they all really fit into the same thing. We have an initial amount times some multiplication factor to the number of compounding periods. Let's see, make sure that fits. Now, this multiplication factor, that could be half-life. So we'd be using half. It could be doubling, and then you would say 2 in there. It could be an interest rate. And the number of times we compound it, the number of times we want that multiplication factor to occur. So when we had our half-life of 10 hours, we said t over 10 because we want every 10 hours to give us one more multiplication factor. In our interest rate for this problem, we said 12t because we want how many compounding periods. We have 12 months in a year. So we multiply the number of years times the months, and that gives us a total number of times that will be compounded. That's it.